There
I
we
got
go.
it? Okay, it's recording. Okay.
I cannot hear you because I need my earphones on. There.
Excellent. It's recording.
Excellent. Okay. Awesome. Okay.
Beautiful.
Okay. Mathematically modeling Corona-19. Moving into this. So mathematical modeling is the technique of finding a mathematical model to portray a physical event. So it's more than just creating a model to match previous data. For example, there has to be an analytical basis for the model, so it'll be useful, so we can play and tweak with things and stuff like that that actually has some bearing on reality. So with enough parameters, you can fit anything. I can have something like 650 parameters, and I'll fit absolutely anything, but none of the parameters will actually mean anything. Each of these parameters should actually match some physical form of reality. So from COVID-19, we're saying that this is exponential growth, and that comes from our belief that the more people who have it, the faster it spreads. So that's all it means, which means we're now in exponential growth, which everybody hears about and so forth. So there's a lot of data to support. We can use a model based on exponential growth. But there's a limit to growth. We have pure exponential growth. An infinite number of people will catch this disease, and there's only so many people in the population, and the disease basically runs out of people to infect and therefore burns itself out or runs itself out because people, we believe, build up an immunity eventually, which is basically true, particularly with this. You may possibly re-get it, but that's quite a rare occurrence from what we've seen. Most people will actually gain an immunity to it, and it'll burn itself out. So for this model, I, the capital I, will represent the number of people infected. K will represent the growth rate per day. That's how fast this thing growing per day. N will represent the number of people not yet infected, which is very easy. That's the population minus the number of people infected. I, little I, represents the time step of each day. So when we build the model, we know that the change in the number of people infected is equal to K, the growth rate per day, times the number of people who are already infected. That makes it exponential. So our formula is very easy. Each time step, number of people infected equals the previous time step of number of people infected plus K times the number of people who are infected, et cetera, at that time step. And we throw on, so that we don't have an infinite number of people who get infected, we run out of people, and that's basically, this is called a taper. So we just throw a taper on the end, and this is, here's my mouse, this is my mouse here, is my mouse showing up? No, my mouse doesn't show up, that's too bad. Okay, so basically the 1 minus I over N is a taper. As soon as I reaches, number of people infected, reaches the grand total of the number of people left to be infected, as nobody's left to infect anymore, that factor becomes 0 and kills it, and it just remains there, and you end up with a nice S-shaped curve, which is how that works. So the growth rate is actually the probability of contracting the disease. That has two factors. One is the probability of contacting or being in contact with a carrier, and the other is the probability of catching the disease from the carrier, or basically K equals is capital E, which is probability of contacting a carrier, times P, which is the probability of catching the disease from the carrier. We already know what K is, so we could just plug that in, but we can get more information understanding if we can see what K is and play with it to see how we might get that. The probability of contacting a carrier is how many people we're in contact with, is what that factor is. The probability of catching the disease is pretty well a constant. And I've just set that at 90%, which maybe it's 30% or whichever, but this is a highly contagious disease, so we'll just throw 90% as a number in that and just see what happens in the model. The other important point that's necessary is called the lag time. Now, the lag time is the time from getting an initial symptom to the time of resolution. And resolution of the disease is you're either dead or you're recovered. So it's either death or recovery. So death, I'm saying the lag time is about 7 days. The recovery is a lag time of about 14 days. So average in there is when resolution is, I guess. The death rate looks weird. This is not, we would expect that the death rate would be something like the number of dead or the number infected, but that's not really what it is. Much, much more useful. And the reason that they have been posting a death rate a particular way is the number dead divided by the number of dead plus the number recovered. And the reason we get that is because the number dead plus the number recovered is approximately the number of people infected about 10 days previously, which means it's the number of people infected minus the number of people who are in hospital, if you think of it that way. Okay, if that, yeah. It works out that it's beautiful the way that it happens. So very nice stuff happens. So far, with all the research going on and all the panic going on and all the promises of having a magic cure or everything else that's happening, there's only one procedure that has had any effect whatsoever on the spreading of COVID-19, and that is quarantine. So far, that's the only thing that works and the only thing that has any impact on it whatsoever. So we can apply the effects of quarantine and show how social culture and relationships with governments can impact the spread of COVID-19. So we'll just do that. There's our model. This is Italy. Now, what do we do here for Italy? So we're going over the value of K. Here's our K1 over here. I've had a few of these things tossed in there, but basically the probability of contact is 1.6 in 1, so it's even a greater chance than it's 50-50 sort of thing is what the odds would be. So E, now I'm saying is at 1.6, which is where Italy started out. P, probability of contacting it, is at 90%. And then as a result, we end up with an initial K factor, initial growth factor of about 9.54. So in other words, almost doubling every day at the very beginning. Here we have K, there's the formula. We started off with 3 at the very beginning, and there's our formula, which I put in, and there's the taper to kill it at the end. So we'll take a look at that, and something quite remarkable happens here. And I'll just go in and show, here's Italy's, there's the raw data from Italy. Here's the total number of cases. So we see how the cases grow, and they're not even coming to an S curve. Maybe there's been an inflection point about here, and I'll show the importance of this inflection point. Perhaps it's kind of dying off a little bit, it seems. But if we now switch to logarithmic, this is quite remarkable because it starts very, very rapidly at the beginning. The slope of this line here at the very beginning is the growth rate at the beginning. But now they've gotten practically flattened off. It's not, they only have about a 4% growth rate here, starting off with about a 90% growth rate at the beginning. So obviously something's happening. This is a huge factor in how quick are people going to respond, because in all other places, that's a straight line. Okay, so the people of Italy have managed to get their frickin' act together, and they have actually made a major point. And this is very much for the unity of the country, how people operate together. Okay, we get everybody to react. That's a huge thing. New cases. Here's active cases. We expect this to go up and then drop again, which is nowhere near that. Total number of deaths is interesting because we go logarithmic. We again see this scale that matches. Basically, the growth rate matches with this. The death rate, we do have this as new cases versus recovery. This is the death rate here. This is very important. I'm going to ignore this part at the beginning of the model. I'm coming in, so this has a reverse curve on it, starting low and then getting, this means the hospitals got filled up and everybody's kind of on their own is what that means. At the beginning, the hospitals can kind of cope. So we've got a death rate low of about maybe 25%, jumping up to about 44%. I expect everyone in the world will hit this death rate. It looks to be coming up to be quite common. So that being, we will return to other cases here in a second. Where am I? Let's go back to the model. So we're back in the model. So what I can do is I can model the change in the growth rate, because the growth rate is dying. So this is now the model of how the growth rate is being killed. There is our death rate. Our death rate has gone up to about 45%, starting at about 29%. The number of deaths will be about 250,000 people will die, and eventually it will hit about 130, 140,000 people will be actively having the disease at any one time. Is the number of people, you can think of them, that are sick, and the hospitals have been completely ruined. But look, this number, which I'm calling the education rate, they managed to lower they managed to lower the growth rate by 6% a day. That is huge. Okay, so they've really kind of gotten on top of this, but they had to play catch up, and there are a number of places that are playing catch up. So if we go over to the world is now going to become a really interesting place. So we're in the world past 1 million people. We can now calculate death rate versus recovery rate. I showed you how to do that on what the death rate is, about 30%. Total cases. If we look here, do we have logarithmic? This is our logarithmic. That's pretty well linear. It started big, then got kind of linear. It looked like it kind of got, and then it got out of hand again, is how that looks. And again, the death rate being logarithmic, they match, okay? So the death rate's pretty well going to be the same. Now that's about all I got on this one. So I now take these numbers and we throw it back into the model. So here we are, the model for the world. Basically, our death rate is costed about 23%. And the growth rate, there's been a slight change in the growth rate, which I gave the benefit of the doubt. So people are learning with about a 2%, I'll say, education rate. Now, the reason this is important is because we're seeing 3 billion people at a time who will be sick. We're talking about 800 million deaths. Total number of cases eventually will hit about 3.7 billion people. It's pretty well the population of China at the present rate if things continue the way they are. The reason this now needs to go up, if we put this up to Italy, and this is what I want to show, if we can increase this to, let's say, 3% to see what will happen, we see there is now a massive reduction. World deaths are still pretty high, but now we only have 1.6 billion people by going from 2% up to 3% of this education rate. Let's go up to 4% and see what that does. At 4%, they've killed it, right? This is the 50 million people now is our deaths rather than the billions, and we've killed it down to 35 million active cases. Okay, with a total number of 250 million eventually. Let's move that up to 0.5% to increase that, and now we've killed it because that's more people. That's fewer people than the number of deaths that we've already had. We're now down to a total number of cases is now down to 4.5 million, and number of active cases is now less to 1 million people. So this number here, which I'm calling the education factor, or it's a factor of how the society acts in a united way to kill this thing. If we go beyond that to where Italy was, which was at 6%, 0.06. This is Italy showed this could be done. We've now pretty well killed it. Okay, this thing could be over very quickly if we can get that to cut down. Canada's got very interesting situation because Canada is now ahead of the curve. If I go to the data for Canada, give me countries. So Canada's not far down here. Canada, here we are. So Canada, we can calculate the death rate, and the number of rates is only 15,000. Believe me, it's in the early days. Here we have logarithmic. This is still linear. I'm not, is drawn off a little bit here, but nothing to write home about. It's starting a bit of an S curve, but there's reason for this. People are still out running around, and it's very, very early days. The reason I know it's early days, let's see, active cases is still going up. This thing hasn't even gotten out of the starting gate. Total deaths, if we go logarithmic, it's still bang on linear. The death rate, can we look at the death rate? Our death rate is pretty well solidly level at about 8%. So hospitals are kind of on top of it in Canada. The hospitals are not filled up and people are not dying in the street, literally. So now I can take this data and toss this into the model. Unfortunately, it shows we only have a 2% learning curve. So we're still really early in the game, but we're kind of stupid on this. If we now click this up to, let's say, 3%, if we change that to 3%, what happens? We could only have about 5,000 people and we've killed it. So a very, very small amount of an increase, the cooperation of the public and actually education level, which could actually kill this for Canada if we get onto it early enough. So that would kill it instantly. So actually, rather than throwing a whole mess of money into research, throw a whole mess of money into public awareness. That will make a difference. That will actually kill this disease. Now we're going to have some fun, because now we're going to go to the elephant in the room, which is the United States of America. And this will show it more dramatically than anybody. So we are now in countries. USA is number one. Are they ever? And this beast has now gotten out of the starting gate, and it's flexing its muscles. Death rate is now at about 30%. Growth rate is still kicking in there. Maybe there's been some reaction in the last few days, but not by much. This thing is still going on. We go logarithmic. And sometimes, maybe more or less, it looks like maybe they're getting a little bit on it, but they're now going to be approaching 1 million people. Okay, fairly quickly looking at this logarithmically. Active cases in the United States, now this thing's a beast. It's still well on its way. Total coronavirus deaths going logarithmic, that's linear. It's, actually it was less, and now it becomes more, maybe less. It depends. And I can't get death rates over a period of time. So that's some of the data that I need to get. That's not being published. Let's return to the model. And as we go to USA, we see that the USA, if they continue, they've got, and I've given the benefit of a doubt of a 3% education level, but they're late to the game. They're playing catch up right now, which means if they continue with this, there will be about 75 million active people sick at any time. The total number of people who will get this will be over 160 million people, which will be like half the population. The death rate will hit about, call it 61 million people. Over 60 million people will die. Death rate is now constantly at about 36%, actually, didn't show it that well, which is about where people will kind of end up. This is our K value here. So America right now is at a growth rate of about 12%. So it's growing 12% a day, but that fluctuates. It could be, let's see, that it could be between 30%, 29% to about 12%, around 15%, which is sort of the average of the globe itself. So as a result, at the beginning, it was doubling every day when nobody knew it was around. And then very quickly, it has dropped. The growth rate here, this is not fast enough to be able to have any effect, and it's going to cause a lot of people to die. So if America can get its act together and hit the same case as Italy, let's say we go up to 4%, we throw more money into public awareness, and instantly we've dropped it down to 10 million people. And our number of deaths have dropped from 60 million down to a little over 20 million. If we now give even 0.5% of awareness factor going into this, we've now dropped it to 600,000, which may be reasonable. That may be as far as America can get it. The death rate, I don't think is going to change. So we're at this much. But if we hit what Italy did at the 6%, they pretty well killed it. You will have 50,000 deaths, only about maybe 33,000 people will be sick at any time, and the number of cases can go off at about 140,000. These predictions that it could hit 100,000 people are woefully out. They're completely and totally wrong. That is if you really get your act together and you really get people to stay in. So where I'm now, I'm going to stop the share here, because looking at the model and the world data, I'm saying the biggest factor now are in education of the public, so that everybody has a true understanding of the situation. Society must work together with a united culture. A small change in the increase of credibility by leaders has a huge effect. And on a global scale, a very small sum of effort in knowledge and education saves tens of millions of lives, like right off the bat. but a very, very small effect, a very small effort can save tens of millions of lives. And the mathematics shows that this is a fractal. All countries follow the same pattern. The only difference is in the speed of reaction, like how fast can the country unite to fight this thing? And that's what the mathematics is now telling us. And that's the weather for today.
Can I ask some questions?
Yeah, definitely. That's what this is about. Let me just kill this off.
Okay.
Okay. Yes, sir.
So in terms of time scale, so depending on what that value is, the K value,
Yes.
so that changes the amount of the amount of the population.
It changes the K value. The K value is not a constant. The K value, if we can change the K value, that has a huge effect.
Right. So on average, I mean, this is probably something that needs to be checked out, but on average, what percentage, if we don't do the right thing and
Yes.
and we don't self-isolate,
we're a bunch of dumb bunnies. Yeah.
Yeah.
We don't learn.
What amount of the population will be infected? Like, is that part of the model as well? So
it could be depending on the death rate and stuff, but the number of people infected won't have anything to do with the death rate. The world average is about 15% a day. Canada's above that right now. We're at 20% a day growth rate. The United States is about almost 35% a day, but it fluctuates a great deal. At those rates, all you're changing is how fast it will affect you. But even if you get K down and you don't change it, you're going to get pretty well the same number of people are going to be infected in the end. It just takes longer to get them. Okay?
Okay.
And that's, less than half the population. So if you've got a population of 35 million people, you may well end up with 10 million people who have had this thing by the time it's able to run its course. That's just the math.
Exactly. I mean, there's a lot of death rates being thrown around, which are actually just the formula of total cases over
total deaths over those who are impacted.
Exactly.
Yes.
So I mean, that would make the case fatality rate down to 2.2, 2.5, etc. And so obviously that's not correct, because that's why you use the formula of for the case fatality rate to be total cases over closed cases. So the closed cases being the dead or recovered.
Dead or recovered, the total deaths over the closed cases.
So in that case,
it's easier to mathematically model it. It's easy to get that data. We can get that number. We can model it. But it's scary when we say there's a 30% death rate.
Well,
what
exactly.
we mean is this. And it may be different because you have to subtract the number of people who are sick.
Most websites actually use the proper formula as opposed to the old formula. But the old formula is what was basically given out to the public at the initial outset of
It's a better number. It's actually a better number. I follow that number because it's easier to work with. It has more meaning to it. It means how much the hospitals are stressed out, and it may go from, well, in Canada, it's only 8%, but it'll hit 45%. I'm telling you that death rate, the way it's calculated, will end up at about 45% because the hospitals can't take it. Right now, America, New York hospitals are on the very verge of collapse. Washington's gone beyond it. Washington State is saying that they're full, and they've been full for.
So as soon as that becomes the case, the CFR death rate will shoot through the roof.
Yeah, it will stabilize the way that I've calculated, about 45%, roughly 43%, and around there.
If it keeps the way it's going now. But,
if it keeps the way it's going.
But over time, with isolation, it'd be interesting to map how long isolation can make the okay.
You see, people also, another thing is you get to this inflection point and you think it's over. Oh, we've got it beat. No, don't go outside. Right at the peak, when you get zero death growth, zero growth in the rate of it and so on, that's the time when you're at halfway point. That's a halfway point.
Right. So the growth rate for United States must be huge at the moment.
Oh, yeah, yeah. It's at like 35% a day, 20% a day. But it's hard to kind of find, and that is a reflection of how much the American people trust their government, are willing to cooperate with the government and cooperate with each other and so on. Right now, it's every man for himself. And if it's every man for himself, that is the worst possible thing you could do.
Excellent. Thank you so much, Bruce.
Yeah.